Welcome guys. So in this video, I want to talk about quantum Fourier transform. So actually you can Google and find Wikipedia page, right? But in this video, I just want to explain in detail and just basically explain the Wikipedia in words and add my own interpretation. Okay, so the quick definition is that summarizes that somebody will give you x, right, which you can write as a computational basis if you want. So it's like a xii, right? Let's say, and then you, after the so-called quantum Fourier transform, then you get so-called y is basically yii, and yi is equals to, I should say yk is equals to, let's say, x n w n n k n from 0 to capital N minus 1. So this is the definition, and that's omega n will be the capital N roots of unity. So you take the capital N roots of unity and then you power to nk and n, and then from 0 to n minus 1, and then pick a yk for each coefficient, right? So this is like a linear map. So there's just a matrix representation for the quantum Fourier transform, and these operations are called the quantum Fourier transform. Okay, and the inverse Fourier transform is also obviously is that it's just that xn is equals to k from 0 and minus 1 yk to the minus nk, take a square root, and easy to prove that these two are inverse and inverse of the results. Okay, sorry, there's a square root of n here. Okay, so this is called a quantum Fourier transform. Okay, and if you like to write it as, so you can write Fn as a large matrix if you want. So it's 1 1 1 1 1 1 1 1, and this is omega square, omega to cube up to omega minus 1, and then omega cube, omega 4, omega 6 up to omega 2 and minus 1, and then omega 3, omega 6, omega 9 up to omega 3 and minus 1. And the final is omega n, it's omega n minus 1 to n minus 1 up to omega n minus 1 and minus 1. Okay, so easy example can be just seen as the wiki. There's this is F4, right? And one example is that you can check F2 is basically, I think it's this guy. So this is the Hadamard gate for F2. Okay, so but this is not the important thing. The important thing is that in a quantum there's a, so the theory is that there's a, so it seems like that this Fn is a obviously n by n matrix, right? Okay, and the theory is that there's a quantum circuit perform. Okay, I should say a quantum circuit with only the elementary operation. There's an easy, like only use 2 cubic gates with an elementary matrix. Perform the, is this a polynomial? I should say the log n, and I think it's log n square. So there's a polynomial log n square. So basically, you only need log n square gates, right? So there's a polynomial. The number of the quantum circuit can choose to be log n square, which perform the QFT, quantum Fourier transform. So that means the QFT is efficient. Efficient in the sense of number of gates. So you only need like a log n square to perform it. Okay, so that's why we will see it in the Wikipedia or other textbook. So this is the standard quantum Fourier transform. The derivation is very long, but I want to mention the key idea, the key points. The key point is the why this line, and this line will give you such results. Okay, so Hadamard is defined to be this, and this is the RM. So R is the control phase. Means that if somebody give you 0, you get 1, and if it's 1, you get this. Okay. Okay. So the idea is that we first explain why these circuits will give you the right hand side, and we prove that the right hand side will combine of all the right hand side will give you a quantum Fourier transformation. Okay. Okay. So let's introduce a notation. So the notation is point. So this notation is that if I write 0.x1, x2 up to xn. So that means this is x divided by 2, x2 divided by 4, x3 divided by 8, and up to xn divided by 2 to n. So just some notation. Okay, so let's see the final line. Why final line give you this, right? So let's say xn. So it says that if xn, once you add a hard mod, you will get this. Let's check this. Okay, so if xn is 0, you get h, right? You get 0 plus 1. For the 1, you hard mod, you get 1 over square root 0 minus 1. Okay? And this guy, by definition, is xn divided by 2 from this point. So this is just 1 over square root 0 plus exponential pi I x n 1. Okay, so it's easy to see that if xn is 0, this is 1. If xn is 1, then this guy is exponential I pi, so it's minus 1. So this is this agree. Okay. Okay. So the next thing is that we check for a second row. I should say this is the last row, right? And this is the next to the last row. Okay. Okay. So it's, let's say this guy. So this guy, this xn minus 1, right? At the mean with the hard mod will be as what we said, 0 plus 1 and exponential 2 pi I 0 xn minus 1. I think everybody noticed this. Then if you use the control R2. So that means if xn is 0, then you get original 1, right? If xn is 1, then you will get the additional phase, right? And this additional phase is exponential to 2 pi I, and this is R2, so it's 2 square. Okay, so that means the final state will be 0 plus 1 plus exponential 2 pi I 0 xn minus 1 times exponential 2 pi I. But this is 2, right? This is so it's 0.0 xn. And combine these two, you get 0 and exponential 2 pi I 0 xn minus 1 and 0.0 x minus is 0 xn minus 1 xn. So and 1. Okay, so by definition, this is just xn minus 1 divided by 2 plus xn divided by 4. So you see, this is xn. So you see, it's obviously this will give you this. Okay, so and so on and so forth. So finally, you will get these two. You will get the 0 and this guy. Okay, so the final thing is that once we get this, the rest, right? The rest is to show all the product of right in your product will give you the QFT x1, x2 up to xn. Okay, so right, this is the proof. So finally, it rests to show that QFT will give you the circuit as the circuit results. Okay, unfortunately, this proof is so long that I don't want to write. So yeah, so I just explained why this is correct, and the proof is just this. So you can go to Wikipedia and type quantum Fourier transform, and you can see the proof. Okay, so the final results is I want to say is that if we can take n to be log 2n. Sorry, we can take small n to be log 2n. So you see, if from here we have total from here we have n minus 1 gates, n minus 2 gates up to 1 gate. So the total number of gates will be 1 plus 2 plus n minus 1 plus 2 plus 3 up to n minus 1. which is n minus 1 divided by 2. Okay, so this is O(n) squared, right? So remember large n, if you take a log 2n, it will be n. So you only need a log 2n squared. Okay, so gates. So to prepare this so-called quantum Fourier transformation, which is easier efficiently. Okay, so in the next video, so we already introduced the quantum Fourier transform. So quantum Fourier transform can be used applied into the famous Shor's algorithm and the hidden subgroup problem and the discrete log and so many other quantum algorithms. So one can view the quantum Fourier transformation is like the heart of the major quantum algorithms. Okay, so in the next video, I will talk about quantum phase estimation, which also use this quantum Fourier transform. And you guys can go to see my Shor's algorithm and discrete log algorithm is already used the quantum Fourier transform. Yeah, so this is just like a technical video which explain why this is true in this small content. And finally, just check. Okay, I will see you guys in the next video. Be sure to subscribe to my channel. Thanks.